Hello everyone and welcome to the channel. So in this particular video we are going to discuss about enantiotopic, diastereotopic and homotopic protons. Okay. Now this particular topic is a little different and it's little vast. Okay. We are going to discuss actually about the stereochemistry from the organic point of view. Now this video is going to be very important if you are preparing for let's say IIT JAM, CSIR NET or GATE exam. So this is going to be very important topic from all of these exam point of view. So I'll just tell you quickly that what are the things which are going to cover, which we are going to cover in this particular video. First of all, we are going to understand the prochirality, right? What is prochirality? And then we are going to understand that how a particular molecule can be said to be enantiotopic, diastereotopic, or homotopic. So how you can say that two molecules, or what is the relation between them? Okay. Then after that, we are going to discuss that how NMR spectroscopy is gets affected by these prochirality or these enantiotopic, diastereotopic, and homotopic type of protons. So that's why I have written protons because we are also going to discuss about the NMR spectroscopy of these particular groups. And later on, as I used to do in my videos, I'll be taking questions which have been asked in previous years of CSIR NET and GATE exam, right? So let's start with it. So first of all, let me tell you that what a chiral carbon is. Now we all know that if a carbon is attached to four different groups, let's say A, B, and let's say C, and let's say not C, I'll be just making it something, let's say C dash and D. If these are the four different groups attached to this particular carbon, we call it a chiral carbon, right? Now, if I remove a particular group and at the place of that, if I just bring up the similar kind of group, that means if I bring up D over here itself, now this carbon, the previous one was chiral, and now this carbon is called as prochiral carbon. Okay. Now this particular group has a prochirality. That means it is a carbon which could have been a chiral carbon, right? So it's a step far from the chirality. That's what it means. So prochirality is nothing but if two groups on a particular carbon are same, that is said to be prochiral. Okay, now you can again remove one more group and replace it with the same group, and then it will be called as prochiral. But we have to deal with these prochiral carbons only. Okay, so now we are going to understand that what happens in the prochiral carbons. All right, so see, I'll be taking few examples quickly just to make you understand in very short. Okay, because I don't want this video to be little longer. I just want to explain everything in short and in a very precise manner. So just be with it. All right, so let's say we have this particular molecule over here. Now, the thing is, we have to find out that what is the relation between, let's say, this H1 and H2. What is the relation between them? Now, from here, we are going to understand that what is enantiotopic, diastereotopic, and homotopic protons. Okay, so what is the relation between these two? So, to understand that, the basic way or the trivial way of doing this is to just replace one of the group with some other group and then see the relation between them. So what I'm going to do is I'm just going to replace, let's say, both of these hydrogen one by one with any of the group. Any group you can take. I'm going to replace it with some halogen, let's say X. Okay. So if I replace H1 with it, so what I'm going to get is something like this. Okay, the stereochemistry on this carbon, I'm not changing that at all. So that is going to be as it is. Now, what I'm going to do, I'm going to replace this H1 with some group, let's say X. Okay, and this is H2 as it is. And now what I'm going to do is, again, I'm going to make a molecule in such a way that, so if you look upon these groups where this X is, I have just replaced these groups. So these two molecules are actually the same molecule. If you just rotate this particular sigma bond by, let's say, by 60 degrees, sorry, 120 degrees, so you are going to get the same molecule. Okay, so these two groups or these two molecules are nothing but same. Okay, so these type of molecules, when when you exchange these hydrogens and then also you are getting the same structure back, or both of them are identical structure, then these two hydrogens H1 and H2 are said to be homotopic protons. Okay, homotopic protons. Now remember, I am just talking about H1 and H2. Rest of the hydrogens or whatever groups are there, I am not talking about them. This is just relation between these two hydrogens. Okay. Similarly, now I am going to change my this molecule a little bit and let's see what is the relation we are going to develop now. Now what I have done over here, now you can see that I have replaced this hydrogen with a methyl group. Now as I have done this, I have introduced this methyl group over here. So again I'm just going to look upon what is the relation between H1 and H2 again. So same step I have to do. That means I have to replace this hydrogen with some group. So let's say I have replaced it with some X, some halogen. So again I'm going to get these two structures, right? Now if you look upon this, now you are not going to get the same structure if you rotate it by some angle, okay? So that thing you are not going to experience in this case. Now if you look upon this exactly, so what it is actually, that if you put a mirror plane over here, you are going to get the same molecule. See how it will look. So if you put a mirror plane, you are going to get something like this, okay? So the one which is above the plane, that will go below the plane, and the one which is below the plane, that will come above the plane, okay? And this is H, and we have CH3 over here, and then we have, let's say, so we will be having hydrogen and the other group. Okay, so now you can see that these two molecules, these two are like, this is nothing but this, right? They are same ones. So that means the relation between these two molecule, or these two basically, is what? They both of them are mirror images of each other, or you can say that both of them are enantiotopic protons, okay? Both of them are enantiotopic protons. So that's how we have discussed. We have done homotopic protons when we replace the group and we got the same identical structures after replacing it. Over here in this particular case, after replacing, we are not getting the identical structure, but here we are getting the mirror images, okay? So that's why we call it as enantiotopic protons. Now let's change this molecule, this particular molecule, a little bit, and then see that what we are going to get. All right, so now if you look upon this molecule, what I have done, I have replaced this hydrogen with some group, let's say hydroxyl group over here. So this particular carbon has now become a chiral carbon now, right? This carbon is now a chiral carbon. Now since it is a chiral carbon, and what we are going to do, we are going to replace these two protons on this particular carbon. So once I have replaced it with X, I have replaced H1 with X, and the other time I have replaced H2 with X, okay? So H1 and H2 is nothing but both of them are protons only. I have just labeled them H1 and H2 just to show you that, yeah, these two are, just to make sure that you look upon it properly, okay? But yeah, what is actually happening, that I have made this particular carbon a chiral carbon. Now once this becomes a chiral carbon, and if you change any of the groups on the next carbon to it, so whenever you have a chiral center already, and the adjacent chiral center, if you make any changes on that, then the pair of the things which you get are diastereotopic. That you should know. And if you don't know, you can look upon it as well. I'm changing H1 first of all with this halogen X, and then I'm changing H2 with some halogen X. So what is happening now? If you look upon these now, you cannot get the same structure by rotating as well. Okay, you will not get the same structure if you rotate. Similarly, these two are not mirror images of each other. Why? If I just show you the mirror image, so the mirror image will look something like this. See, the mirror image, in the mirror image, it is true that H2 will come above the plane and X will go below the plane. But here on the back side, your hydrogen will come above the plane and OH will go below the plane. So are these and this same? No, they are not. Okay, so that means these two are not mirror images of each other. So you cannot say that these are mirror images. So what is the relation between these two? So they are diastereotopic. Okay, diastereotopic. So diastereotopic protons. So this is how we identify two protons or two groups to be homotopic, enantiotopic, or diastereotopic. It's pretty simple. For homotopic, you just have to see that after exchanging whether you are getting the same like the same molecule or the identical molecule. Then enantiotopic, if you get the mirror images, and diastereotopic if you do not get the mirror images. One more way of identifying diastereotopic is if the adjacent carbon is a chiral carbon. In that case, you will always get a diastereotopic protons. Okay, so that's what the way is to do it. Now this was a trivial way. Now I'm going to discuss the shortcut method, or using the group theory, how to identify and how to tell that two groups will be homotopic, diastereotopic, or enantiotopic. Okay, so I'll be just giving you some rules, and but just by the use of those rules, you can easily tell between two groups, that whether they will be enantiotopic, diastereotopic, or homotopic. So let's discuss that. All right, so let's discuss about, this is a rule, or you can say this is the shortcut way how to identify that a particular ligands or particular, I have written ligands, you can discuss about protons or any groups, two groups, whether they will be enantiotopic, homotopic, or diastereotopic. Okay, so see, if the ligands, if you're discussing proton, you can replace ligand with proton. So if ligand or proton are exchanged by axis of symmetry, okay, that means if there is axis and that can exchange those two protons, in that particular case, those two protons are called as homotopic in nature. Okay, those two protons will be homotopic in nature. All right, the next one is if the ligand are exchanged by plane of symmetry. If you apply a plane of symmetry and then those ligand get exchanged, in that case, those ligands are said to be enantiotopic. Okay, those ligands or those protons will be called as enantiotopic protons. Then if the ligands are exchanged by the center of symmetry, okay, center of symmetry means if there is inversion center in the molecule. So if they are exchanged by that particular center of symmetry, then also the molecule or the groups are called as enantiotopic in nature. All right. Whereas if the ligand get bisected by the molecule or bisected by the plane, if you apply the plane and the ligands, the two ligands which you are studying or the one which you are actually trying to find out the relation between, if those two ligands get bisected by that plane, then they are called as diastereotopic. Although this particular condition is not necessary. Okay, this is not necessary condition. Sometimes, or in the most of the time, this is true, this happens to be true, but there are other factors also which you have to take care of. So these three things are very sure that, okay, if you can exchange them with the axis of symmetry, homotopic. If you can exchange them with the plane of symmetry, enantiotopic. If you can exchange them by the center of symmetry, then also enantiotopic. For diastereotopic, if these conditions are not followed and if the molecule get bisected, then you can say that this is diastereotopic. Okay, so this is a general rule which you can follow and you can easily find out a relation between two molecules. Let's take some examples and try to use our like shortcut way or the rule, the like with the help of these rules. Okay, because by exchanging and doing it will take time and that can make confuse you as well. So these rules, if you are good with like group theory or good with applying axis of symmetry, plane of symmetry, center of symmetry, you can never do these kind of questions wrong. Okay, so let's take some questions and discuss them. All right, so let's take these examples to understand that whether what is the relation between the protons shown over here. Okay, so let's talk about the first one. If you look upon this, this is, let's say this is Ha and this is Hb. We want to find out relation between these two. So try to use the first thing. Okay, try to see that whether there is axis, you can replace these two protons with the help of axis or not. So axis you can find from here, and if you rotate it, so you cannot do that, right? Because this side you have phenyl group, this side you have methyl group. So both of them are not identical, and that's why you cannot rotate this by 180 degree. Okay, so this rotation is not possible. So that means this axis is actually not possible. So what you can do now, you can actually form a plane of symmetry. Okay, so if you just apply a plane like this, okay, if this plane goes like this, then what is going to happen that okay, so this particular plane, if you see, so this particular plane is also not applicable, right? Because these two groups are different and these two hydrogens are different, right? So you cannot apply that plane, but there is a plane which is possible over here, and that plane is the plane which will contain this phenyl and this carbon, because it's a tetrahedral structure, right? This is below the plane, this is above the plane. So you can find out a particular plane, okay, which will contain this methyl group and this CH and this phenyl group, and it will pass from between of these two hydrogen. Okay, just consider it like this, that these two hydrogens are like this, and your like the phenyl and the CH3 are on the other side. Okay, they are on the different plane. So you can have a plane which will pass in between of these two. These are the two hydrogens, Ha and Hb. So that will pass in between of these two. Okay, so that will cut these two like this phenyl and this methyl part, but this Ha will be below the plane and this Hb will be above of that plane. So they will get reflected in the plane. So basically they this is a plane of symmetry which can reflect these two protons, right? So the relation between these two particular groups or these two hydrogens is what? These are enantiotopic. Okay, enantiotopic. I'll just write down E just to show. So the relation between them is enantiotopic. So if you look upon the relationship, let's talk about Ha, Hb, Hc and Hd. So you cannot do anything with the molecule, right? You don't have any axis or anything, The only thing possible is a plane, and that plane is actually like this. That plane will pass through the molecule in this way. Okay, that means from the centers. So from this particular carbon and from the center of this bond. So this particular plane will go like this, and this plane is going to reflect this HA with HD and this HB with HC. So the relation between HA and D is what? That they are enantiotopic, and similarly your I'll write down like this. So your HA and HD are enantiotopic in nature. Similarly, your HB and HC are enantiotopic in nature. And what I told you that there is no other thing, right? There is no like you cannot have any axis in the molecule. You cannot have anything else, right? And there is no center of symmetry as well. So that means what? Yeah. So that means the other ones, like the relation between A and E, the relation between A and E. This was E and this is A. Relation between these two is diastereotopic. Okay, they are diastereotopic. Similarly, your D and E are diastereotopic. Similarly, your B and E both are diastereotopic. So like that, you can find out relation between all of them. If we come in if we come in molecule number 3 over here again, I'll just show the relation between HA and HB. Okay, so how to do that? If you see, you cannot rotate this molecule. Why? Because these two groups, if you rotate this, if you think that okay, I'm going to rotate this molecule, so after rotation, what you will get is something like this. That these two over here, your hydrogen will come above the plane and your CH3 will go below the plane, because we have done 180-degree rotation, right? So here also on this side also hydrogen will come above the plane and methyl group will go below the plane. HA and HB are going to change their places. So this is not a proper rotation, or this is not allowed rotation. So if the rotation is not allowed, that means these HA and HB are not homotopic. So the other thing which is possible is the plane of symmetry. Okay, so rotation is not possible. So I'll just erase this. So rotation is not possible. Let's erase this up. The only possibility is the plane of symmetry. So if the plane of symmetry is there, plane, how the plane will go? Again, in the same way like it went over here. It will go like cutting these two molecules from the center of these two molecules by like reflecting these two molecules. So HA and HB are what? They are enantiotopic in nature. Okay, enantiotopic. So you just have to look upon plane, axis and center. Center is not anywhere in the examples, but yeah, you just have to look upon that. Here if you come in this particular case, again if you look upon this, now you can have an axis of rotation. Why? Because obviously over here if the fourth group is not shown, but that is hydrogen only, right? So if you rotate this along this particular axis, so there is nothing which is going to change. You are going to get the same thing. Hydrogens are already here. So one of the hydrogen will come above the plane, the other will go below the plane. So nothing is going to make much difference. So HA and HB are going to replace their places through this axis of rotation. That's why these HA and HB will be homotopic. Okay, they will be homotopic in nature. Coming to this particular molecule, now here you can see this is in this particular ring, it's a spiro compound. And if you see this HA and HB, these are above the plane. They are coming above the plane. Okay. Now you cannot have any axis which can rotate and which can which can replace these two groups. So the only thing possible in this case is a plane of symmetry. Okay, that plane you have to imagine the plane passing through the center of these two bonds, passing through this carbon and the center of these two bonds and reflecting these two. Okay, so the plane will be bisecting the molecule in two equal half. If I show you from the top, this molecule will actually look like something like this. Okay, like this, and this is HA and this is HB. So the plane passes through the molecule like this. Okay, from here. So this is your plane. So yeah, this plane of symmetry is reflecting these two molecules. So this is HA and HB over here are enantiotopic. Okay, they are enantiotopic. All right, over here if you see in this particular case, now in this molecule you cannot have any axis. See, if you rotate it along the axis, you have pi bond over here, obviously, which will go to the other side, so you cannot rotate the molecule. If you try to apply the plane which you are applying in the previous question, or in this example, if you try to apply that plane is going to bisect these two hydrogens, and that's what we have discussed in point number 4, that if the plane bisects these two groups, or the two groups are getting bisected by the plane, the groups are diastereotopic in nature. Okay, so here that thing is getting satisfied. So that plane is bisecting these two molecules, or these two hydrogens. So basically these two hydrogens will be diastereotopic. Okay, so that like that you can do lot of examples on this particular topic. You can have many examples, as many examples as you want. I'll be taking some questions from CSIR net. Before going into that, let's discuss the NMR part of it. Okay, so when you were discussing about the NMR spectroscopy, remember that homotopic and enantiotopic, both of these types of proton, they give same, like they will give the same chemical shift values. Okay, so they will have same chemical shift values. Whereas the diastereotopic protons, if two protons are diastereotopic in nature, they will have different chemical shift values. Okay, they will have different chemical shift values. So that's how in a complex molecule, if a molecule is given in a very complex manner, that's how we decide that whether the molecule will be like the protons are diastereotopic or enantiotopic. That will tell you that whether they will give you two different chemical shifts or they are going to give a single chemical shift. Okay, so that type of questions we have in CSIR net, and in the organic spectroscopy we discuss the diastereotopic protons, enantiotopic proton. So there you should be aware about this thing. Okay, so let's take some questions which have been asked in previous years of CSIR net, and let's discuss them all to understand that how whatever we have studied, can we apply that on complex molecule as well or not. All right, so here is a question which was asked in your previous years of CSIR net exam, and it was asked that the relationship between HA and HB, what is the relation between this HA and HB? Okay, and the four options are here: homotopic, isotopic, enantiotopic, diastereotopic. So what will be the relation between them? Now, at once it seems very simple, and it seems like okay, you can apply a particular. So what you have to start? You have to start from the axis. You have to see that whether you can apply axis of rotation or not. So if you do that, if you try to see that if you try to apply this axis of rotation, so actually what is going to happen that these two phenyl groups which are above the plane, after applying this axis of rotation, they are actually going to be below the plane. Okay, so these two groups are going to be below the plane, although these two will not get affected. They will be like HB will come here and HA will go here, and CO2H will remain as it is, but the difference will be that these two phenyl groups will be below the plane, so you cannot apply this axis of rotation. Okay, so axis of rotation is not possible. So what else you have to see is whether you can apply plane of symmetry in the molecule or not. So that plane of symmetry you can apply. Actually that plane of symmetry will pass through the molecule like this. Now don't think that this bond is bent. Okay, this you can take a straight bond. Okay, so it doesn't matter, you don't have to take, because it's a tetrahedral carbon, right? So these two, this bond and this bond has to be on the plane, so they will on the same plane. So don't look upon how it is shown in the question. It is just shown just to confuse you a little bit. So this particular bond, the bond between nitrogen and carbon, and the bond between this carbon and this COH, that will be on the same plane. So that's why they will lie on this particular mirror plane. So actually these two HA and HB will get reflected, and the relation between these two you can easily say that is enantiotopic. So the correct answer will be enantiotopic. One more confusion which can be arised, that what about the stereochemistry of COOH? If you draw that, that might go above like out of the plane, and that is how we can say that this plane is not bisecting the molecule completely. So remember, whenever we are taking this, we are taking all these molecules, other groups except the chiral carbon, we take the other groups to be the point as a point charge, or as a spherical molecule. Okay, so we don't have to take the stereo of this particular carbon. Okay, we are just considering it as a single sphere, just that's it. Okay, so just to make the things more simpler. So these will be enantiotopic in nature. Okay, I hope this is clear to you. Let's take another question. All right, let's discuss this question from CSIR December 2016 exam. And over here it says that the methyl group in the following compound is, okay, so the relation you have to tell over here is between the two methyl groups. So these two groups, okay, it's very simple question. Just by the concept or just by the rule you can easily do it. So you can see these two phenyl groups, one is below the plane, the other one is above the plane. If you apply a axis through this center of this, and if you rotate it like this, so what is going to happen is you are going to form something like this. Okay, so you are going to form this particular methyl group which was above the plane is going to be that side. Okay, or you can show it in the same way, same order, that is this methyl is above the plane and this methyl below the plane, and you can show that this particular phenyl which was below the above the plane, that is going to be below the plane, okay, and the other one is going to be above the plane. So that is not going to make any difference, right? Both the structures are actually same. So that means what? That the relation between these two methyl is nothing but homotopic. So it's as simple as that. You can just do this type of question in just 30 seconds, just by looking into the question, just by applying the axis, then apply the plane. If axis is not applicable, then apply the plane, and that's how you can see. We'll take one more question, and that is going to be the last one for this video. Let's talk about this last question, which was asked in CSIR June 2016 exam. And the question over here says that the following compound, the stereochemical descriptor for HA and HB is. So basically, what they are asking is relation between HA and HB. Okay, so how to do this particular question? See, first of all, you go with the sequence. Okay, try to find out that whether there is axis of rotation or not. Now here you have to be very careful, because this particular whole molecule is not a planar molecule. If you can see, this particular part is coming out of the plane, and this particular part is again coming out of the plane. So this is not a planar molecule, but it's a biphenyl kind of thing, where this group is out of the above the plane and this part is below the plane. So it's not on a same plane, but these two are like this. Okay, they are 90 degree to each other, you can say like that. All right. So fine. So in that particular case, if you talk about the axis of rotation, so you cannot have any axis of rotation over it, because if you rotate it along with this particular axis, so even though HA and HB can replace their places, but there this side you have OH group, this is hydroxyl group, and here you have this much bulky group. They are not going to be like like you cannot rotate and you cannot replace both of them, right? Because both of the groups are different. So this axis is not possible. So you cannot provide this, you cannot apply this axis. Coming to the plane, okay. So that particular plane, if you remember, we have done an example in the starting where we have taken pH group and CH3 group, and we have taken through two hydrogens. One was HA and the other one was HB, let's say. Okay, and we have seen that there was a plane of symmetry. That plane was passing through this pH, and it was passing in between of this HA and HB, right? This HB was below the plane towards the other side of the plane, and HA was towards towards you. So that was on the other side of the plane. So these two groups were on the other side of the planes like this, and the plane was going in between of them. All right, so that particular thing, if you are thinking to apply the same concept over here, that is not going to work. Why? Because see, over here these two groups, this phenyl and this methyl and all the other bonds, they were all planar. They were all on the same plane. So the plane was applied on the same on the same plane on which these bonds were, and the plane was bisecting all these bonds. But this is not possible over here, because if you apply that, this molecule, which is not a planar molecule, if you see this particular part which is above the plane, and again this particular part which is above the plane, will not be bisected equally. Okay, so that plane is again not possible. So this means there is no axis of symmetry, and there is no plane of symmetry. Both of these things are not there. So that means homotopicity is not available in the molecule, neither enantiotopicity is there. Talking about this fourth option, which says constitutionally heterotopic. So constitutional heterotopic means that if you replace this hydrogen, you will get constitutional isomers. Constitutional isomers means cis and trans isomers. So that is not going to happen. Why? Because this carbon is sp3 hybrid carbon, so you are not going to get any constitutional isomer over here, right? So fourth option is also not applicable over here. So the only thing which is possible in this particular molecule is diastereotopic. So these two protons becomes, or these two hydrogens HA and HB, they becomes diastereotopic in nature. Okay, so that's how you can easily find out whether your given protons are enantiotopic, diastereotopic, homotopic, or what is the relation between them. Okay, now question based upon it in the NMR part, you will find out in the organic spectroscopy portion. You will get question where you have to decide, a big question will be given, and you have to decide that whether the protons are enantiotopic or diastereotopic. If they will be diastereotopic protons, they will give chemical shifts at two different places. Okay, so that you have to keep in mind. We'll discuss that in our video later on organic spectroscopy, where I'll be taking some typical different kind of questions which have been asked already in CSIR net and GATE exam from organic spectroscopy. So that is going to be the other topic for some other video. For now, you just remember that diastereotopic protons will give you chemical shift at different places, whereas enantiotopic and homotopic protons gives you chemical shift at a same place. Okay, so that's what it is all about, your enantiotopic, diastereotopic and homotopic. This topic comes under topocity. Okay, so topocity is the topic under which we study all these things. So I hope whatever I taught in this particular video is clear to you. You guys understood it well. And that's all from my side for this video. I'm recording late in the night, and yeah, it took a lot of time to record this particular video. Do give it a like if you like this video. And if you're new to this channel, please subscribe to the channel. And if you have any doubt or if you want to ask anything, you can ask me in the comment section below. Thanks for watching and have a great day. Bye bye.